did the front part on Friday, and the biggest pattern that we noticed was that it was the exponential, it was the multiplier, and we could rewrite the sections in a form of the exponent so that it proved that 2 was our base, so that we could write our equation of the line. Are we good with that part? And that since it's positive, it's increasing rapidly, right? Okay, so go to the back side. See if we can clear that up a little bit. Okay, and this time we want to graph, and I'll give you, because I have the 116. This time we want to graph the number of folds to the area. Okay, so if we go back to our table, which I'll show you there, okay, that would give us an ordered pair of 0, 1, 1 and 1/2, 2 and 1/4, 3 and 1/8, 4 and 1/16, and 5 and 1/32. Okay. Okay, so we know it's a function because there's 1 to 1 for every x. There's only one y. Okay, so what's the domain going to be? Let's shuffle the cards, because you all love them so much. But it's a Monday morning. So, Kaya, what's my domain? Yes, it would be. It would be x is greater than or equal to 0, which is going to be less than or equal to 5. Perfect. Okay, so we're going to let our horizontal be the number of folds. So we would have 1, 2, 3, 4, and 5. Okay. And we're going to have our vertical axis be the area. Since we have everything in like fraction yucky numbers, okay, we're going to label our y-axis by 0.1. Because that's going to get us under 1. So this would be 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, 0.9, and 1.0. What do you think the graph's going to look like? Can you see that? I'm sorry. Is that better now that we have the... What do you think the graph's going to look like? It is going to be exponential. That's absolutely true. Like on the one up here, we started down here and it was going up, increasing. Okay? What do you think it's going to look like with having a bunch of fractions? What's it going to look like? Any thoughts? Is it going to go up? Is it going to go down? You think it's going to go down? All right, well, let's plot and see what's going to happen. So my first one, I'm at 0 and 1. And then for 1, I'm at 1/2, so that's 0.5. And that 2, I'm at 1/4, which is going to be 0.25, so that's going to be about there. You're kind of estimating, and that's okay. 1/8. What's 1/8 in terms of decimal? 0.125. So 3 1/8 is going to be about right here. 1/16. 1 divided by 16 gives me 0.06. So that's going to be about here. So I'm guessing that she's right, and we're decreasing. And one of the things about exponential is that it's never going to cross that x-axis. Okay. It always is going to stay, it's always going to keep approaching 0, but it's never going to quite touch it. Anybody remember there was a special word for that? When a line's going real close and it goes right beside it, but it doesn't actually touch the line. It's like there's an imaginary barrier there. Anybody remember the name of that? Asymptote? Do you guys remember that name? Yes? No? I see some shaking yes, some shaking no. Okay. We're going to talk about them today, so it's all good. Asymptotes actually are fun. That's what makes all the kind of graphs look cool. All right, so we connected with the smooth curve, because it's a function. And let's write the actual function. So if we think about what we did up here, okay, because that's how we found our base, how can we turn our fractions into something with an exponent? What do you think? How can I turn 1/2 into an exponent? Yeah, so I could write it like this. Would you agree with that? Could I also write it like that? Yeah. Okay, so if I have 1/2 squared, that's the same as 2 to the negative 2. If I have 1/2 cubed, that's the same as 2 to the negative cube. Agreed? Okay, so what's my pattern going to be for my function? Isaac, are you awake? Are you awake?
Yeah.
Kind of. What would my pattern be if I wanted to write the function? What's my base? 2. Okay, so I would have f of x is equal to 2. What's the same for my exponents in each of these? It's negative, right? Because it's going down. And so I would have 2 to the negative x. Okay. Now, where's my y-intercept? Yo. I don't have any. Actually, I have a few up here on my desk still. I will take any tissue donations that anybody wants to bring in. Where's my y-intercept? Yeah, at 1. So I get 2 to the negative x plus 1. Okay, and this graph, because it's going down, is exponential decay. Okay, so exponential growth rises up really fast. What's a real life example of exponential growth? What multiplies quickly?
Rabbits.
Rabbits. That's the prime example for exponential growth. They multiply quickly. Absolutely. Okay. What about exponential decay? Any ideas on that one? is kind of the gross one, but huh? Wow, never thought about that, but you're absolutely right. They're there and then they die fast. Yeah, that would be a good thought process on it. Think of that piece of bread, and you have, on the very first day, here's my piece of bread, okay, and the first day, it's got just a little speck of mold on it, right? That's day one. What's it look like day two? Well, it's grown a little bit bigger. And then on day three, it's grown a lot bigger until the whole thing is nothing but green decay of green fungi. It is disgusting. Have you ever done that on a science experiment? How fast the bread decays? The yeast in it makes it go real quick. So, alrighty. So, if we have any exponential function is going to be in the form of y is equal to your base to the x. Okay? If it's exponential growth, it's going to be a positive exponent. And if it's decay, it's going to be a negative exponent. Cool? Alrighty. Where are we time-wise? Okay. This is the next page in your packet, correct? Okay. I had... Alright, that's the last one. Alright, so let's do graphs. You are going to need your graphing calculator for this one. Okay. If you have not gotten your graphing calculator yet and have not rented one or whatever, you need to make arrangements. You're going to need to make arrangements to get that done because you're going to really want it over the next couple. I'm not sure I could do logs without my graphing calculator. No, just an FYI. Okie dokie. So, all right. We did exploration on the exponent functions back in Algebra 1. Okay, and we've already talked about how the base equation is y equals b of x. Okay, b represents your base. And for exponential growth, must be the b has to be greater than 0. Okay. Your input is the exponent, and the output is your y. All right, exponentials have that imaginary line. It's called an asymptote. Okay, it's a line a graph approaches but never reaches. I think of it literally as like a little, when I'm graphing something, I'll do it as like a little imaginary dotted line. Like there's my barrier. It can't go across that. Okay, so to graph all these exponentials, let's use our graphing calculator. Who remembers how to put in equation of a line? Anybody? Corey? Oh, come on. Have faith in your knowledge.
Y equals?
Yep. The little y equal button, because they already have the first part of your function there. Okay, let me clear out what I had. Now I want to do 2 to the x. All right, so I hit the base. I did my little caret to go to up to the exponent, and then here's your x. All right. Now I want a whole bunch of points to plot. Okay. So I'm going to go to the table, which means I hit second and graph, and oh, how nice. It gives me all the points that I want. So 0.25, -1 is at 0.5, 0 is at 1, 1's at 2, 2's at 4, 3's at 8, and 4's at 16. Okay, so now when I plot that, at -2, I'm at 0.25, and I'm just going to ballpark it. Okay, that's okay. And then at -1, I'm at 1/2, and at 0, I'm at 1, and then at 1, I'm at 2, I'm at 4, 3 goes up to 8, and 4 is going to be just about there. Okay. Now, when I connect that line, where would be my imaginary barrier, my asymptote? Where would you think, if I hit, it keeps going closer and closer, do you think it's going to be like right along here? And the equation of the line for that is y equals 0. Does that make sense? It's going to keep coming as close, because think about it. If I go to -100, I'm still going to get a y value, right? And it's still going to be positive. So it's never going to hit 0. It's just going to go really close to it. Does that make sense? All right, so let's look at y equals -3 to the x. What are some of your table values? What did you say, Callie? Ooh, 0.037. Oops, no, 1. -1's at 0.33. 0's at 1. 1's at 3. 2's at 9, and 3's at 27. All right, let's graph that. How do I graph 0.111111111? Any ideas? Go as close to 0 as you can, but you're not going to, it's going to be above the 0 line. 1/3 is going to be a little bit there. These are ones you're going to have to just eyeball, okay? 0, 1. 1 is at 3. 2 is at 9. And 3 is way off the chart already. Do I have another asymptote for this one? What do you think? Liz, do you think I have another asymptote? Where do you think it's at? Where? Yeah, it's still going to be at the same place because it's still going to just keep coming closer and closer, but it's never going to cross 0, so y equals 0. All right, let's look at one more. Between the two that we've done so far, do you notice any similarities?
No, it's not. Zero's always one.
0 is always 1, absolutely. In fact, do you think for this particular, if we do y equals 4 to the x, do you think 0 is going to equal 1? Yeah. So let's change and verify that. And it sure does. So at -2, I'm at 0.06. -1 is 0.25. 0 is 1. 1 is 4. And 2 is 16. All right, so let's graph those points. 1 and 4. And we have another asymptote at 0. Okay, so we've already said our y-intercepts are always going to be at 0, 1. I like that. What about x-intercepts? Do I have any? Do I have I crossed the x-axis on any of these? So there are none. What's a general trend? What do I mean when I ask that? What's the general trend? Any idea? What'd you say? Exponential growth. It definitely is the growth, which means it's increasing, which means it goes up from left to right. Perfect. What about the domain? Anybody got any opinions on that one? Yep, it sure is. It's from -infinity to infinity, because you can keep going out this way. But what about the range? Perfect. Because I'm never going to quite hit 0, so that means I'm just less than. But I'm going to go to infinity. Okay. And what happens to the graphs as my base gets larger? It what? Yeah, absolutely. They get steeper. What do you think a graph would look like if you had a base of like 20? It's going to go up real fast, right? Because think about it. We would have at 1, we would be at 20. What's 2 going to be? 400. That's going to go up super duper fast. And so the larger the base, the steeper it's going to get. All right, cool beans. Okay. Anybody heard or seen the symbol E before? Where have you seen it? Is that something from Algebra 1?
All I see on the calculator is the numbers.
It is on the calculator. Thank God. This is another reason why you need the calculator. Oh, chemistry. Yeah, is that...
Yeah.
Do you guys use it a lot in chemistry? What do you use it for?
Exponents.
But I mean, for, like, what's its purpose?
To make the number, like, you see, I'll start off, like, the entire level, where you can just make it, like, shorter, kind of. Basically, so it's like
Yeah.
a breakdown version.
Yeah, it's a symbol. It's kind of like pi. It's an irrational number, okay, so it never ends and it never repeats. That's the big thing. So if you actually needed to program in, like, multiplying something out, you could never, it's never ending. So they have it actually programmed in your calculator so that you can just put the symbol in, and then you don't have to do all the different numbers, okay? But it's a natural exponential function, okay? So what I want to do is look at the graph. If we change it to E, which is above your ln, oops, I guess it would help if I, and I had it to the x, okay? Let's look at the graph of that. Okay, how does that compare? Actually, let's go ahead and put, all right, there's our e to the x, and then we're going to have 2 to the x, and then we're going to have, whoops, helps if I put in the right base, 3 to the x. It helps if I could, there we go, okay? If E is 2.71, I'm going to expect it to fall in between the 2 and 3. Wouldn't that make sense? All right, let's take a look at it. That was our original E. There's 2. And I see, and then there's our 3. Okay? So it is. It's going to run a lot closer between. What, did I lose you? Your window dimensions. Go to invalid DAM means window dimensions. You hit your window and do it from like -10 to 10. Is your Y at -10 and 10? And your, this is the spacing, so I have it at 1. Really? That's weird. Do what? Yeah, that should still be okay. Okay, so what I would like to do now is I want you to do the same thing, but we're going to do with negative exponents, okay? So we'll go ahead, take it, you guys work individually to compare these graphs, and then we'll come back together. Because this time we're going to look at the negative x's. All right? Sound like a deal?